this is the second of our in a series of language webinars that we're going to have this year. So we had first Jose Camacho Collados last time. Today we have Ivan Vulić with us, and as you can see, we have a long list of interesting talks that we'll be having for the rest of the year. So if you're interested, be sure to let us know, and you can sign up for one of these webinars as well. But today we have, like I said, a really nice talk by Ivan Vulić. So Ivan is currently a research scientist at Google DeepMind in Zurich, after he's been there for a year as a visiting researcher. Still affiliated with the University of Cambridge, the technology language technology lab there, where he spent already 10 years across different roles. So he holds a PhD in computer science from KU Leuven, awarded summa cum laude, and in 2001 he was also awarded the annual Karen Spark Jones Award from the British Computing Society for his research contributions. So he's worked on a lot of things, especially cross-lingual, multilingual, multimodal representation learning, modularity, and composability. And today he's going to be talking to us about merging and MoErging, a mixture of experts merging of models and modules. So we're really, really excited to have him here today. And if you want, Ivan, you can take the floor.
Hi, good afternoon, good morning, good evening. I don't know where people are. And many thanks for the intro and for having me here. I'll share my slides now. Hopefully it will work. It worked previously. And we have a lot of ground to cover in the slightly less than an hour. So speaking of how to structure the talk, so there will be like some sections or subsections of the talk. So maybe I will first give one portion of the talk, and we can have a couple of questions, and then we're going to have it 3 or 4 times, and then at the end, if there's still time, we can continue with questions. So as I said, there's a lot of ground to cover, so I'll start immediately. Right, so basically, we start from the current state of affairs in research, where a lot of the most well-known models are basically what we call a monolith, or at least at the interface level, which means that basically they're like really big, dense models with and we call this the monolithic wall. So they are massive, they're ever growing with more and more parameters. So whenever you have to change something in the model, you probably need to retrain, and this is like very expensive, etc. So adaptability of those models is very limited, because they're quite rigid. So if you want to really specialize in a specific task or a specific distribution, you probably need to create like a full copy of the model. And then if you have many isolated copies of the models, they're all specialized for certain skills. So how do you combine those skills to have this like know-it-all type of model that we seem to have? So then how we interface with the model, it's often through now like just inputting text or documents into context of the model. So it means prompting and in-context learning, but it has its own limitations when it comes to adaptations of these models, which is, it's often inefficient. It has limited performance for like more complex things. And that's one of the problems. Then if we want to specialize in multiple skills at the same time, what we often face are the standard problems of multitask learning or sequential fine-tuning, which means in multitask learning, tasks might actually have detrimental effect to each other. So if they actually have conflicting requirements, etc. If we do sequential fine-tuning, it often results in catastrophic forgetting of previously acquired skills. So like continual learning is one of the large problems with current state-of-the-art models. Right, so one way to tackle this set of problems is through modularity, which is one of my favorite areas of research. And when we talk about modularity, it's like a very abstract high-level concept. So we can talk about many different parts of modularity, even like starting from the supposed modularity in the human brain. But in this context, we're going to talk more about task modularity, model modularity, and touch a bit on data modularity. So basically, when we talk about data modularity, it means basically keeping distinct data distributions separated or like at different locations, etc., because it might be due to some access rights, or like the data can be private, proprietary, license. So you don't want to mix all the data together. So if we mix all the data together, we're kind of creating multitask framework at the level of the data. So if we keep the data separate, we can actually learn separate parameters on separate data distributions, which means that we can create modularity at the level of tasks as well. So we can basically separate modules and models that are trained on specific data distributions, and then the idea is to combine skills coming from these different data distributions so that we achieve positive transfer and still have this like clear separation between data and tasks. And when we talk about model or module modularity, it is very much linked with task modularity. We can have specialized computation components that we can recombine, reuse, recycle, and this is in the core of this talk. Right, so why do we want to break this myth of the monolith in the first place and have this modular vision? Basically, because if we actually create small modules instead of big monolithic modules, we can actually have much faster adaptations, because once you have a very strong generalist model, it is kind of not obvious, but it is expected that we can quickly adapt to something that's more demanding. So if you already know something quite well in general, you can maybe just like zoom into a specific distribution. And so for example, if the model knows a lot of languages, it might be much quicker to adapt it to a new language and things like that. Another interesting point is this continual aspect, where we want to seamlessly integrate new knowledge as it comes, without the need to like reset, retrain everything from scratch, and without this catastrophic forgetting. Then another interesting aspect is collaboration between different teams. So if we actually have specialized components, they could be asynchronously created or improved via different teams, and then just combined or composed or merged together, which is also linked to the fourth point in this slide, which is decentralized asynchronous development and training, also in data distributed setups. So modularity is also quite connected to federated learning, etc. So here's just like a list of research areas which are all related to modularity and model merging. So I'm not going to read all of them. This is more like for completeness, and I'll be mentioning these keywords across the talk quite often, or at least some of them. Right, so let's start first with what is a module. So in the title we had modules and models. I mean, my opinion is that specialist models can also be seen as modules. So there's no real clear distinction between modules and models. But what I define as a module is sort of a computation unit that encapsulates specific knowledge and does specific computation. So that's roughly that. Yeah, so this is something that I already said. Essentially, anything that forms a distinct, often parameter efficient, it doesn't have to be computational unit, for a specialized purpose can be a module. So we can then talk about modules operating on the large model at many different levels of composition. So the first level, or the first type, is the so-called parameter composition, where, I mean, the way the neural networks work is that they have weight matrices or weight tensors that actually that depict certain functions that operate on inputs and create certain outputs. So one way to modulate the function of the original model is basically to operate this modulation directly on its parameters, meaning changing parts of the parameters, or some of them or all of them, in a way to skew the model towards a certain specialization, which is different from what the model does when it doesn't have this module. So this is parameter composition. So and one prime example that pretty much everyone has encountered in their work now is low rank composition, or LoRa. But we can also modulate the output of the layer in the network and the final network also by manipulating the input of the network. So basically you can prepend or append or even interleave certain extra trainable tokens inside the actual input tokens, and this will, if you change the input with the fixed function, it will actually change the output. And this is the idea behind some other well-known techniques like prompt tuning, prefix tuning, and in-context learning and RAG could be seen as like discrete symbolic instances of this specific idea. And then finally, the third idea is the so-called function composition, where this module actually basically has its own separate function that processes the same input as the one that goes into the main model, then creates a different output, and then you somehow need to aggregate or choose the output from these functions. So adapters, as very famous path models, it's one type of that, and mixture of experts and experts in MOE architectures are also like functionally composed with the generalist main model. So it's all different sides of the same story. This is the more formal slide that kind of tells what I already talked about. So basically, when we talk about parameter composition, we change the weights parameters of the actual network that operates on the input X. If we talk about input composition, we add something to the input X. It could be like continuous embeddings, or we can operate at the level of the actual discrete symbols and discrete tokens. And then there's the function composition where we feed the same input X to two different functions and then somehow combine them. So, and typically the main idea is that when we train these modules, we fix the large generalist model and just optimize the parameters of the module, be it doesn't matter whether it's like parameter input or function composition. So this is basically modularity in one slide. Right, so I'm not going to talk about LoRa because I'll just assume that people know how it works. I will just briefly introduce task arithmetic because it's very important for model merging. And basically, the idea is that every single specialization or fine-tuning of the model can be seen as just like a delta change from the original model to the target model, and it's a delta change in its parameters. And this change is called like a delta vector or a task vector. So basically, you can create a task vector for every single fine-tuning by just subtracting your original source parameters from your target parameters. And if you create this vector, you can actually do task arithmetic, which means that you can add, subtract, interpolate between all these different vectors, and this is the so this is the main ground for model merging at the parameter level, as we'll see later on. And I just want to mention something about LoRa and task arithmetic. So what LoRa basically does, it's just a low rank parameter efficient approximation of this delta or task vector, or rather task matrix, and that's all it is. Then there's another idea which does sparse subnetworks, which means that only certain parameters are required to actually specialize the big model towards certain behaviors. So if we actually sparsify our delta or task vectors, we actually get standard sparse modules, which are also found in the literature. So we can say that sparse subnetworks are basically just a sparse or pruned approximations of the full dense task vector. Anyway, this is just like a quick detour. Now going back to sequential and parallel adapters, I'm mentioning this because I just want to emphasize how similar they are to actual mixture experts. So basically, adapters are just functions inserted into transformer layers, which can be inserted in a sequential or serial fashion, where first the input X goes through the standard original transformer, and then the output of that function is provided as input to the adapter, and then adapter adapts that, and this is the final output. Or parallel adapters are basically functions applied in parallel to the original model's function. So so those are two main things. And basically, when we talk about mixture of experts, they are just they're basically adapters of much larger size. And the function is typically not combined with the base model function, but we rather choose which function to apply instead of the original model's function. So there is this component called router that I'm going to talk about later on, which basically chooses which module to to take based on the input. So for example, if the input is something related to code, you can choose your code expert and it will process code rather than choosing your Danish speaking expert and things like that. So and those experts are typically put inside the specialized replacements in feed-forward network layers of transformers. Okay, so I could take one or two questions here if there are any questions before we continue.
Any questions? If you have a question, again, either raise your hand or write it directly in the chat, and you can do it this way.
Okay, there is something in the chat.
Nothing, no questions right now, though. Anything else?
Okay, then we can continue. So we've kind of defined our landscape of modules, and the next question is, okay, if we specialize for certain expertise or certain skills, how can we combine that expertise into a single model? Because if we create many different copies and many different modules, it also bloats in terms of storage requirements and memory, and it's basically not scalable. So we need solutions that will go back to monolithic models, but with upgraded skills in a sense. Right, so then we talk about module and model compositionality, and as mentioned before, this is related to many areas like multitask learning. So we want like a single model that masters multiple tasks, continue learning, adding new skills as we go without the need to retrain everything from scratch. Then also out of distribution robustness, meaning that if we combine several skills, the model might actually become better in another skill. So if the model, for example, if we have a simple robot that has a module and which knows how to turn right, and then another module that knows how to go straight, then the model can actually have much more complex trajectories than the one that can go only to the right all the time. So basically, this is when we talk about out of the domain, out of distribution robustness and positive transfer. And yeah, so basically, the central question is how to combine the knowledge stored in these modules to solve new tasks and to adapt to new inputs. And yeah, and then we can talk about two different types of composition. So one is basically the so-called input conditional or dynamic combination, where at inference and runtime, based on the input, you select which expert is going to process that input, or a selection of experts. And this is quite flexible, and yeah, it has fine-grained control. And the main component of this solution is basically the router or the retriever, which actually tells you, okay, use these experts to process this particular module. Another even like simpler idea, which is becoming more and more popular in the literature, is this like static global parameter level combination, where basically you can imagine that you have two modules or even two full models that are experts in different things or have some things in common, some things are different in them, and then you try to combine their parameters offline before inference and then create or like merge into a single unified model which is of the same size as the constituent modules that actually went inside this parameter level combination. A good thing here is that you don't need to keep many different experts ready to process the inputs. You just have, again, like a single model, so it actually prioritizes inference efficiency and deployability because you don't need to change anything structure-wise in the model, basically to serve this new merged model. Right. So now I'm going to delve deeper into these two types of compositions. So first, starting from this dynamic input conditional composition. So as I mentioned, the key component here is the router, which basically has to tell the signal where to go in like a very high level sense. So the router is this function that assigns certain weights to possible trajectories to different experts or modules or models that we have as part of the architecture. So those are these like alpha coefficients, and in the standard mixture of experts architecture, the router is actually learned jointly with the experts. But the difference to standard mixture of experts and the thing called MoErging or modification is basically that we want to learn this router post hoc, meaning that somebody and this enables decentralized asynchronous development. So imagine a scenario where people create different experts, like even models of different sizes, and they just give that to some like central repository, and now we need to learn this router function that will just learn where to route the signal when it comes, so that the code goes to a code expert, mathematical input goes to a math expert, etc., etc. So in that sense, router can be seen as sort of a retrieval function. Based on the input, you need to retrieve the most suitable experts that will process your input. Right, then we have different types of routing. We can talk about fixed routing, which is basically you just decide on routing pretty much in advance. So one example is basically multilingual routing. So if you do language identification on the input and you know, okay, my input is now in the Croatian language or my input is in Basque, I will just use my Basque expert to process that input, and that's it. So you don't need to kind of do dynamic routing through the network, etc. Then yeah, a more interesting thing are these like learned routing mechanisms, where we can again talk about two different subtypes, soft learned and hard learned routing. So you can already imagine what this is based on these figures. So soft learned routing is basically avoiding to make any discrete decisions on the selection. So it just assigns a vector of weights for all the experts that you have. So basically, you're just learning a probability distribution over the available modules. So you can see that so you always have a probability. So we have 3 experts here, and we learn a probability distribution. So you can see a problem here, which is related to scaling, which means, okay, but what if we have 1,000 experts, or like very fine-grained experts, and what happens then? Then we have to pass our signal, our input to all of them, because every single one has a certain weight, and then we need to kind of load all of them into the memory. It's like with 1,000 experts, it's 1,000 forward passes, so it becomes quite problematic. Okay, so in the classical sense, this mixture of experts is really like a proper mixture of experts, where we just when the router assigns weights, we process the signal with every single router and then combine them using the weights assigned with the router. And yeah, all modules are always activated, so that's a problem. Okay, so what one can do is, once the router assigns those probabilities or weights for every single router, you can actually make a discrete decision and activate only the top K modules. So it is still soft learned routing, because we still assign those probability values, but we limit ourselves to taking only the top K modules, so that we don't have to forward pass through all of those experts. Right, so that, for example, here we decided not to go through the trajectory that goes to the expert 1. Right, so a special case of top K routing is basically top 1 routing, where it's basically just applying argmax, so just select the top module and push your signal only to the expert that has the highest probability weight. Okay, so another decision that one has to take is basically sort of like the level of operation of routing, which means that we can actually we can apply routing at the token level, meaning that for every single token in the sequence, we will have a different decision on where to route that token. And there are like some problems with that strategy, because it often happens that one expert tends to take a lot of these tokens, and then there is like the so-called load balancing solution, which tries to uniformly distribute tokens across not only hardware accelerators, but also across different experts, so that we don't have overcommitted and undercommitted experts. So this is like a trick. But speaking again about the granularity of making this decision, so yeah, we can do routing at the level of tokens, which means for every single token, we need to choose top K experts, or we can do expert level routing, which means for every single expert, choose the top K tokens and do the assignment that way. And the most expensive thing is basically, okay, let's just have all the information like a global information, and then try to decide the optimal expert token assignment based on this complete information. But yeah, it is not really used in practice because it's just too computationally demanding. Okay, I kind of send. So yeah, example level routing is basically at the sequence or example level where all the tokens of a specific sequence are routed to the same expert. And this routing can then be achieved based on like some metadata. So this is what I mentioned when I talked about like routing BASC examples to the BASC experts. So you can just do language identification, and then okay, this is the BASC, this is the sentence in BASC, send it to the BASC expert, or you can try to do pooling on the token representations and then do some sort of like similarity metric between expert representations or expert embeddings and these like pool token representations, and then based on the similarity you make your decision. Right. Of course, it is possible to do hybrids in routing, so you can combine fixed and learned routing based on where you are in the network. So you can, yeah, so you can actually have, you can even have different experts at different layers. So some experts will be language experts or multilingual experts, and some other experts will actually be experts at the level of domains. And then you can actually decide to do different routing for different specializations, basically. Oh, so this was a very much like a crash course in routing, and now we're going to move to static global parameter level combination, often called like model merging in its stricter sense. Right, so, but before that, we're going to make a transition from routing to merging via MoErging or modification, which is sort of like an in-between scenario. And the main idea here is what I mentioned before, is that it's about reusing existing library of modules and experts, because people create models all the time. They put them on Hugging Face, and some models are better for certain tasks with certain inputs, etc. So is there a way to just fine-tune this router and learn the router that will just tell us which expert to use with which input signal, and this supports addition or removal of modules because they all exist in some central repo. So if we actually add more modules, we just need to redefine the router function so that it takes this new module into account, and this is the main thing, right? So there is a very nice paper which actually creates a very comprehensive taxonomy of MoErging or merging modification methods from Yadav and colleagues. And basically, they say that there are three key decisions that one has to do, make when doing merging, which is basically how and where to get your expert. So how the expert is designed in the first place, because not all experts are actually amenable to all routing mechanisms. Then the second decision is basically how to route, how to learn your router. And the third thing is how and where to apply your merged models. So whether the application is basically in domain, in the same task, whether it's like out of distribution, you're trying to do zero-shot inference, etc., etc. And the large design space, so there are so many methods now that do some sort of merging, and what they actually claim and show in the paper is that a seemingly wide diversity of methods, if you create your taxonomy in the right way, we're going to talk about that very soon, all these methods are actually very similar to each other, even to a fault, some of them. so there's often like a single small design choice that is like a core differentiator between two seemingly completely different methods. And what is often the problem in this literature is that many of the methods, because they seem completely different, they don't compare to each other, so the comparisons are often inadequate and incomplete. Right, so here is roughly, so this is taken from the paper, like a taxonomy of methods starting from the expert design. So basically they have two subsections here. The first one is the expert training, which means expert training is sort of standard means let's create a module or a model without any modifications that make it merging aware. So this means like, okay, if somebody just trains standard LoRa's, there's no any merging aware, additional merging aware mechanism inside the standard LoRa. So we need to deal with routing based on standard LoRa's. Or some methods actually do custom expert training, meaning that they kind of anticipate that those modules will be merged after training, which means, for example, you can add some sort of like a gating function or an extra embedding that will capture the representation of the module, which could be used for learning the routing mechanism later on. Then the second design choice is the expert data privacy, and there like there are two assumptions, and then methods differ based on that assumption. So we can, so one assumption is like the federated learning assumption, where the data is kept private, so you can't really share the data. So you can learn modules or experts on top of the data, but the data cannot really change its source, and we can't give the data from one source to another source. So it's just not, it's not possible to share it. And another assumption is like the more lenient one, where the data is basically shared, and all the expert creators can see all the data also from the other experts. Right, so then when we go to the routing design, as I mentioned, router is basically the critical component of all these systems, and then methods can differ based on the data set that is used to learn the routing function. So there are even approaches that try to learn routing based on internal representations of the experts themselves. So it's basically no routing data set at all. Some methods assume, so this target thing is we have data for the target task, and we can use that data to inform our learning of routers. Then the third option is we actually can use the data that was used to train the experts to also train the routers. So that's probably the strictest, the most lenient setup, because we can easily reuse the data, but just now except or instead learning the experts, we can now learn the routing function, but we have access both to the experts as well as to the data that created them. So we have clear separations of distributions used for learning those experts, etc. Or you can use general auxiliary data for that. Then when we talk about routing input granularity, so this is something that I mentioned before. So we can actually do token level. So this is what they mean by step level. So every single token can have can be routed to a different expert, or we can route at the example level or sequence level, where the whole input is routed to a single expert, or we can have these like fixed routing decisions where we like for at the level of like a full language or a full task, we always route to the same expert. Then routing depth granularity is another decision, which is basically whether we do different routing strategies at the level of different layers in the model, or we always have this like global routing decision at the model level. Expert selection, this is also related to what I talked before, which we can have, I called it soft or hard routing. Here they call it dense or sparse routing, where basically dense means we always have this probability distribution of weights over different experts, and sparse means that we're just going to do a hard cutoff at a top K experts, and that's it. And then finally, how we aggregate experts, this is very similar basically to our figure before between dynamic and static compositions. So output is basically dynamic, which is very similar to what mixture of experts are doing. And parameter level composition means, okay, select your modules and then do merging at the level of parameters. So this is this model merging in its stricter sense that we're going to talk about very soon. And finally, there's this application design, which means what are we trying to use the merged model for? So it could be for trying to actually improve generalization of the model by combining knowledge of all these different experts. And this generalization could be done in domain for unseen examples of the same task or a set of tasks, or we can try to go completely out of distribution and try to master a new task without seeing many examples or any examples of that task. And then when it comes to seeing or not seeing examples, we can operate in zero-shot setups, few-shot setups, or even assuming like a full training data set for the target task. And so basically what this paper did was creating a catalog with design cards, and then they assigned that every single design card with these properties to every single method that existed at the time of writing that survey paper. Right, so now we're gonna smoothly transition from MoErging to merging, although in a stricter sense, merging was covered already here when I talked about expert aggregation at the parameter level, so there's not a fine line. Yeah, so basically I took those two quotes just to kind of trying to demonstrate how people think about MoErging versus merging. So I would say merging is a narrower term, and strictly speaking, it tries to make language models acquire new capabilities by assimilating parameters from homologous models without retraining with GPU. So you have several models, and then you're trying to combine their parameters and see if you can create like a combination that will work really well in general and for all the tasks which are actually covered in the constituent models. Right. So the first main idea is extremely simple, and it often works really well. So there's a paper called Model Merging at Scale, which basically shows if you scale up the models, what often works quite well is just simple linear weight averaging, which means, okay, take the parameters of the first model, take the parameters of the second model, and just average their weights. And this new merged model will actually be quite good in both tasks. It might lose some performance for the first task skill, it might lose some for the second, but it might actually be quite okay in both. And this works despite all those non-linearities in deep networks. And does it always work? Yeah. So we'll see. Well, yeah, we'll see if it always works. So and then when we talk about parameter level merging, we can talk about intra merging, which means that as we continue fine-tuning the model, we create different checkpoints of basically the same independent run, and we can merge those things, and they will improve generalization capabilities of the model. This is the so-called model souping type of merging. So no, it's basically checkpoint type of merging, and we can also merge checkpoints from independent runs of the same model, and this is the model soup. So we don't have to throw away suboptimal independent runs. We can merge them with better runs, and this will actually create a better, more generalization savvy model from which is a pretty interesting finding. So there's like a really nice paper called Model Soups that analyzes this. So one condition is that weight averaging is only possible when fine-tuning after pre-training, and the main reason for that is the so-called linear mode connectivity property or principle in the weight space. We'll discuss this in a little bit. If you actually start even with the same architecture and then you do complete pre-training, which is very long, etc., etc., you can't really merge those models via simple averaging because they actually move to completely different loss landscapes, and that's it. So basically, when we talk about task arithmetic, we can merge these like deltas or task vectors rather than full thetas, which are like full parameters of the model. Okay, so why does parameter level merging work at all? So I would say there are two main reasons. So the first one is overparameterization, which means that given that these networks are so large, etc., they often have redundant information in those parameters. So even if we change some of the parameters, there might be like another part of the network which can still do pretty accurate predictions about the same type of input. So basically, we have redundant information in across many parts of the network. So even if we destroy some of it, some of it will still be preserved. And another, even like more important aspect is this linear mode connectivity. And basically, the idea here is that despite all the non-linearities in the network and like very complex curvatures of losses, etc., basically of areas of low losses or like good solutions are often connected via simple linear paths in the loss landscape, which means that if we actually do interpolation between two models along a similar path, they will often end up again across the same path of low loss. So we want to actually get out of the low loss landscape. So this is this third figure here, which means that if we have if we have two models that actually ended up in having seemingly completely different solutions, if we average them, we're again gonna end up in part of the loss landscape, which also is a low loss solution. And that is a very interesting empirical finding. So there are papers about this. So I just cited two seminal papers, but this is actually what makes model merging and weight averaging magically work. Right. So, but I mean, there are problems because, I mean, you can already imagine what problems we might expect when we just do simple weight averaging. And it means that if tasks that skills that we want to have in the merged model are orthogonal to each other and have some conflicting requirements, those tasks might actually cancel each other. So you might imagine like having a weight matrix. Imagine a weight matrix where every single value has the same absolute value but a different sign. So if we just simply weight average those parameters, we will just end with like square zero parameters across the whole model, and that model is worth nothing. So basically, the idea of a lot of continuing work on model merging is how to avoid this interference, which means preserve as much knowledge as possible in the parameters of the model, but decreasing the possible interference that comes with entangled weights. And yeah, so some of the potential solutions are basically trying to do some sort of like structured updates where you select which part of the network will get updated and which one will not be updated. So you can imagine, for example, two sparse subnetworks where the actual indices of parameters are completely disjoint between the two networks, so they will have zero interference by design. Or you can talk about structure sparsity, etc., etc. Another interesting concept is the so-called weight disentanglement, where you actually have like a regularization function before fine-tuning that tries to really keep weights as of two or more tasks as separate as possible. And this is another possible solution. Or a very well-known post hoc solution is the so-called ties algorithm. So I'm just going to briefly go through this algorithm because it's very simple to implement and pretty well known. And it tries to deal with some interference problems that I mentioned before. So the first problem with interference is that like low value parameters often negatively impact if you weight average. So you can imagine that a certain parameter is like very important for task number one, and it's very unimportant for task number two. So like task number two will probably have a very low value for that parameter. So if we just blindly average, it will decrease the importance of the parameter for task number 1, which means that this parameter will actually, if we do it for many parameters which are very important for task number 1, it means that we might not be able to process task number 1 so well anymore. So the first thing that that this algorithm does is basically trimming task vectors. So you take the delta, you take your task vector from your target values to your source values, and then you remove deltas which are below a certain threshold. It doesn't have to be both like positive and negative values, so it's by absolute value. And then you need to do some step number 2, which is called elect sign, because if you have large values in opposite directions, those might actually cancel each other out. So basically, if you're merging n models, you are choosing the dominant sign for every single parameter value. Once you choose the dominant sign, you are erasing all the parameter values which are opposing that dominant sign. And then finally, you just merge the models, because now you don't have any conflicts. So you just do like disjoint merge of the remaining parameters, and that's it. So the problem with this algorithm is that it potentially removes plenty of useful information, and as the amount of models grows, it will remove more and more stuff, because it just looks for commonalities between all these different specialized experts. Okay, so then there are more advanced ideas. I'm not going to go into details here because we don't have the time, but let's just say that there's now like a strong incentive to try to use the knowledge coming from SVD decompositions to figure out the dominant directions of change, etc., etc. So I'm just listing this paper called Knots as one prime example of this line of research, but yeah, there's no time to go into that. Right, so again, going back to MoErging versus merging. So here we have this like hybrid combination where, although like parameter level merging is typically done offline, we can also do it online, where basically a router selects the experts that we need for processing that input, and then we can apply the merging parameter level function on top of these experts and create this merge expert that will process this particular input. So there's no reason not to do that, but right now there's no clear benefits over this more standard output level composition when the router is used rather than doing parameter level merging, because then you lose all the perks and advantages of doing offline parameter level merging. Right, so now what I have listed here is just some examples of modularity and compositionality in use, with like some like representative architectures where this is used. And I'm not gonna go into details of every single paper, because this is more like a broad overview, so that I convince you that this is like a very interesting and attractive research topic. So this paper from Rameh et al. Is basically how to use merging to recycle multiple checkpoints of the same model, and how to act better initializations via training on auxiliary tasks, and then combining those auxiliary tasks into a non-random minute that you then fine-tune on the target task, etc., etc. So basically, in order to fully explain every single of these images, I would need a couple of minutes. I'm not going to go into details here. But they cover some of the like standard processes. Like vanilla fine-tuning basically means just fine-tune on the target task, you're done. But model soups are basically fine-tuning multiple models on the target task, and then you just merge. Or you can use also like auxiliary tasks, so you can fine-tune on many different auxiliary tasks which are related to the target task, create different non-random models that you use as different non-random inits, which you then use for fine-tuning on the target task. You could create like n fine-tuned target task models, and then you do model merging, and this model will typically be better than all the other alternatives here. So this is like model merging. So this is like branching and then merging here, for example. Right, so another particularly well-known use case of model merging and combining modules is basically cross-single transfer, where the main idea is to create language-specific modules and task-specific modules, where you disentangle the knowledge from the language, from the knowledge from the task, and then you can swap your language with another, your source language with another target language, and this network with a target language module and a language agnostic task module will be able to process that task in another language. So basically, imagine that you have a named entity recognition system where you have data in English and you want to port it to Swahili. What you can actually do is basically swap the English language module with the Swahili language module and keep the task module for NER trained on English data, and this should work to some extent, which is pretty interesting. So then there are papers for zero-shot out-of-distribution generalization, which try to recombine LoRa modules from a library of, or growing library of LoRa modules, and without any specific routing data. So going back to, this is like a prime example of MoErging. So there is this like arrow paper, which is pretty interesting because it does routing solely on the basis of internal structures of LoRa's. And I spoke about method cards before. So here is the method card for this particular solution. So yeah, expert training means standard. So we just have LoRa's. We assume we don't have access to expert data once the experts are creating. We have zero routing data sets. So we're just using SVD decompositions and singular values from SVD decompositions to singular vectors to do the routing. Input granularity is step, meaning token by token. Depth granularity is modules, so we actually do routing decisions differently at every single layer. Expert selection is sparse, meaning that we just have top K routing, and then they aggregate at the parameter level, so they choose LoRa's and then they merge it into a final, and they try to generalize to out-of-distribution tasks, and the user data set is fully zero-shot, so they don't assume any task data. And then there's another paper that tries to do exactly the same thing, and their model card is very similar. So the only real difference is basically that they make training of LoRa's also merging aware, because they add these extra gates while training LoRa's, which they fine-tune after fine-tuning the LoRa. And this is this Fat Goose paper. It's also like a very nice paper to read as well. Then there's a bunch of work in mixture of expert architectures, which I called branch, train, do something afterwards line of work, where basically you upcycle different experts, you train them on specific data distributions like code math, I don't know, different languages, etc., separately, asynchronously, and then you're trying to bring them back, so merge them back afterwards, because that way you kind of allowing exploration and exploitation via branching and merging. And a lot of work has been done recently in this line of work. So I'm just mentioning some of the papers here. So there is this branch train mix. There is also, I think this one is called Nexus, and it's the variants of the same idea, basically. And here's another example. I won't go into details, but how model merging and modularity can enable creation of distributed language models, where basically you can keep your data distributions completely separate, and you can exclude or include experts on the fly at inference, so that you keep all the knowledge from specific distributions in specific experts, and that way you don't really leak any information to other experts, which means that everything stays very privacy savvy. And this is a paper from called Flaxolmo from AI2 recently published. You can also use model merging for improving reward policies in RL reinforcement learning with human feedback. So, sorry, there's a typo here. And there's another really nice paper called Warp, which actually shows how you can do different flavors of model merging to improve your reward policies and reinforcement learning eventually on top of LLMs. And yeah, so basically, what are some of the open challenges? Yeah, dynamic versus static composition. I don't have the time nor energy to now go through all of this. I don't know if people will be able to read this. I can actually yeah, share the slides. So
that'd be great.
yeah, yeah, there as you can see, just yeah, you can read it for yourself here. There are many open challenges because this is really like still an emerging area, and the traction in 2025 was really good. So there were so many papers that just came out in the last 6 months or so on merging and MoErging. And yeah, so some of the ideas is like, can we be flexible and combine the ideas behind dynamic aesthetic composition, where you can actually decide to merge parameters or create another expert at every single layer of the network if you have a budget that is larger than that is basically in between a single model and n times single model when you merge n models. So that's one idea. Then we haven't even touched this, like how do you merge completely heterogeneous model architectures? So for example, you want your llama merged with your Gemma model. So there is a emerging line of work on this, where the key concept is this transformation from one model to another. But this is, of course, non-trivial. There are some people working on this. And it comes with many different related research problems. It's like how to align different tokenizers. What about merging at the final output instead of merging at the level of representation? So we can talk about multimodal distillations. What about Franken merges? Some people actually worked on combining transformers and Mamba type of architectures. And yeah. And another interesting question is basically this modularity from the get-go. So because we are kind of operating on monoliths still, because we're not training modular models from the very start. So if we create our pre-training models to be more like merging aware, maybe it will actually facilitate merging after their initial pre-training. But this is, of course, like a very expensive endeavor. So I don't know when we're going to see some ideas in this front beyond mixture of experts, which are used already with like DeepSeek, for example. And yeah, so as usual, I think I packed too much content for my own sanity in a single talk. So I will just have 3 more minutes for questions. Sorry about this.
No,
Yeah.
that's great. It was a really great talk. I mean, like I said, there's a ton of information here that I think we'll have to have some time to unpack, but it's super, super nice. So thanks for that.
Yeah.
Any questions from the audience? You have to be fast, huh? So you have 3 minutes. No, Bashir, have you? No. So yeah, I mean, one of the questions that I had was, I think you touched on it right at the end, was this interesting thing of merging models that have very different architectures, and picked up on the Mamba versus Transformer, something like that. But I was thinking of something even more extreme, where you have, let's say, some old school LSTM that was just super fast to train and happened to work really good for a specific task. And if you wanted to merge that kind of information into, let's say, a larger model, is there any research that's going in that direction that you're aware of, or?
I would say that people are trying to maybe do something at the level of more like output distributions, which is more like ideas related to distillation. But architecturally, or if we go to the actual like components and representations, it becomes, I think, very difficult, because it's like completely different. So I think people just use those proxies. Basically, you have the interface towards both models. They actually output some logits. So maybe, yeah, this is the right level where you can do some merges. But yeah, so I'm not aware of any work that tried to merge like an LSTM with a transformer, but it might be possible. Yeah.
Okay, thanks. Let's see, Marcus, you have a question? Hi, Marcus, by the way.
Yeah, hello. Yeah, I've been discovering one direction of research in this field, or looking at it lately, which is kind of going in the other direction of MoErging. But as you briefly mentioned, aggregation of experts and the mixture of experts layers. And from what I've been looking so far, I get the feeling that it's kind of a pretty under-discovered field at the moment, and that there's to me at least, it seems like there's much less research on it than the promise that it could provide. Like, we're doing distillation of really large mixture of experts models, when maybe instead, if we were good at it, we could actually do some inter expert merging for specific tasks, so that you'd go from having DeepSeek 600 50B to, or whatever, to like 300 or 200, but with the same performance for some specific set of tasks.
Yeah, I haven't seen much work in that space. Yeah, because I think people are still kind of primed in like the classical mixture of experts way of thinking, and I don't know, like some potential ideas would be like creating a lot of experts for like very fine-grained use cases, and then gradually merge them so that you try to balance the performance of I don't know. So it might be better than just cramming all the data together, like, which is maybe different distributions or semi-different distributions, and learning like a small number of experts. Maybe we can actually specialize really aggressively and then gradually make them less specialized as we go, and come to a better place than starting with coarse experts. So I think aggregation and like this more like dynamic aggregation of experts is something that is, I think, underexplored, as you said. So yeah, that's a good point.
Let's see, maybe we have time for the one tiny last question, which is from Girish Kushik. They ask, does model merging work for different modalities, basically? So let's say a LLM with a pre-trained vision encoder, something like this.
I mean, if you align the semantic spaces in which they operate, or they have some shared components, for example, if you have a multimodal model that can process both like text only or text and vision, and you can merge some of the components so that actually the same model can do vision. But if you have heterogeneous architectures, and then, I mean, it's a complicated answer basically, but yeah.
Okay, perfect. Right.
Yeah, but if you just take like a separately trained vision encoder and separately trained LLM and try to merge them, yeah, it won't work, because the way you process images, it's completely different. So it's a lot of bells and whistles, basically.
Yeah. Okay, great. So let's thank you again. Thanks again, Ivan, for being here today, for a really great talk. And it's a pity that we couldn't have a little bit more discussion, but that's what
yeah, thanks a lot. It's often weird to just sit alone in the room and give a talk, but this is how it is. Yeah.
All right. Maybe next time we can see each other in person. All right. But thanks a lot again. All right.
Thanks a lot. Thanks a lot for
thanks
having
everyone
me.
for coming. Everyone.
I need to dash off now.
Absolutely.
But thank you. Bye.
Okay. Bye. All right. Bye, everyone.